I'm excited to share a breakthrough in real-time filtering for load cells and bridge sensors that we've been working on for a while now. For those of you developing real-time control and measurement applications, the challenge usually centers around how to maintain fast transitions to sudden changes, how to suppress mechanical oscillations, how to reduce measurement noise without losing detail, and more importantly, how to do all of these things in real time with minimum latency. It would seem that these requirements often contradict one another, as improving one usually worsens at least one of the others. For many of you, I'm sure that you've tried to filter your signal with a simple moving average. Although the moving average is an excellent smoothing filter, it's a terrible low-pass filter with very poor stop band attenuation. Although increasing the length of the moving average makes the filter much more sluggish, which slows down the transitions, so it's not really ideal for many industrial measurement applications. There are, of course, many other filtering methods, each with their own pros and cons, but I'd like to share a new approach that builds upon the simplicity of the moving average. By cascading multiple shorter length moving averages, we can build a Kolmogorov Zurbenko or ZK filter cascade. A key point here is that we can use shorter moving average filters with fast transition performance and then improve the overall high frequency noise cancellation performance by cascading them with copies of themselves. Comparing the frequency response of a long moving average filter to that of 3 shorter moving average filters in a Kolmogorov Zurbenko cascade, we can see that we've dramatically improved the stop band attenuation, thus improving the frequency domain performance while keeping the transition width wide for tracking our changes. So we've got the best of both worlds. We've got something which has excellent time domain performance and excellent frequency domain performance. This unique property forms a large part of the wizardry of the solution and achieving the performance that we're discussing. But you're probably thinking that there's more, and you're right, there is. Although the ZK cascade provides exceptional low-pass filtering performance, its passband extends down to DC, meaning that it will also pass very low frequency oscillations, allowing slow disturbances from structural sway to creep through. Therefore, by cascading a median filter after the ZK output, we can address these residual issues. Operating on a sorted buffer and selecting the middle value, the median stage rejects slow and sustained deviations, such as structural sway, resulting in a much more flatter signal, which is ideal for our needs. Designing the filter cascade in the ASN Filter Designer and loading a test dataset, we can see the final result, which is pretty good. Adjusting for the cascade group delay and superimposing the input over the output, notice that transition tracking is fast, with no overshoots or undershoots, and all glitches and low frequency oscillations have been successfully suppressed. So there you have it, a real-time hybrid filtering solution for load cells and other bridge sensor applications that exemplifies the principles of real-time edge intelligence, delivering intelligent physics-informed processing without the reliance of machine learning. I've added a link to the application notes, so please have a read and let me know what you think in the comments section below. Cheers, and I'll see you next time.